Project Feed 1010 is pioneering a crowdsourced network of scientists, teachers, students, and farmers to optimize aquaponics, a sustainable food production solution that combines aquaculture, fish farming, and hydroponics, growing plants in water, to support year-round crop production with up to 90% less water usage than conventional agriculture. This is Project Feed 1010.
You may have believed that a mere Starbucks cup must serve one very simple purpose. However, our goal at the Institute for Systems Biology is to minimize our ecological footprint and promote the upcycling of everyday used items.
Every mission has brains behind the operation. These are ours. Nitin Baliga, Senior Vice President and Director. Serdar, Senior Research Scientist. Claudia Ludwig, Education Program Manager. Jake Valenzuela, Postdoctoral Fellow. Jessica Day, Project Coordinator.
These people and other researchers at ISB work together to teach 18 high schoolers from across Washington about sustainable agriculture and aquaponics systems, with the goal of having this education spread beyond the walls of ISB and into their own communities.
Project Feed 1010 was really kind of a perfect fit for this because you can have a global impact by educating all the high school students and also raise awareness for sustainability and issues around the food security.
Their first task was to create a roadmap of interconnected communications via cell phones to push them to look at problems with a systems approach. The students then received the HUGE challenge: Hydroponic, Upcycle, Grow, Educate. Huge for short.
Anything could be this kind of system, right? And that's what the huge challenge is about, is to get the students to be creative and figure out how could they design their own systems from everyday household items.
Then came the preliminary setup. We scavenged workbenches and containers all over the lab for used tip boxes for about a week. We decided to use tip boxes because the lab goes through them extremely quickly, using hundreds weekly for all kinds of experiments. We became creative and realized that they are a perfect fit for a hydroponic system.
Building began immediately.
Tank water was used to keep the systems hydrated. Unlike tap water, this water comes from fish tanks. This brings along loads of different nutrients and bacteria that help keep the plant alive without the added use of fertilizer and without harsh chemicals like chlorine that's normally in tap water.
We used coconut husk as an alternative for soil to hold the plants in place. 18 students, 36 systems. Where would these micropipette environments grow? What better place than a closet on the outer part of our lab? After being built and covered for a few days to allow germination, the systems were ready to be measured for growth. In order to extract water and measure nutrients, a small hole was poked in the bottom left corner of each system.
We measured all 36 systems every day, each one having its own trough as a home for its water. We used a syringe to sample water from each system and cleaned it using distilled water after each measurement.
The measurements began. In order to do this, we used strips that tell the amount of individual nutrients when lined up against a key. We measured ammonia, pH, alkalinity, chlorine, nitrite, nitrate, number of plants, and the average plant height. The students were also able to monitor their systems and shared in the failures and successes that come with experiments.
One of the things that ISB taught us was some of the challenges and the importance of aquaponics.
Even the negative results are something that you can actually play and change and learn. Even though those are really frustrating times, and I think solving these problems at the end really gives you the satisfaction. Maybe they understand even if growing this basil in this small box is difficult, imagine how you can feed all these people.
One of the systems was used as a control and grew basil, and the other was up to the student.
Someone even grew avocados.
In just a few days, growth was obvious, and some even survived to become full-grown plants.
So you can really develop this project into educational component, scientific component, and also maybe social component.
To both implement this in a classroom setting as an acting model of the nitrogen cycle and other ecological concepts. We're also going to provide an opportunity for other students to not only learn about sustainable agriculture through this, but also be able to build these systems themselves with hands-on experience.
So if you guys start thinking about it now, you can really be part of the solution in the future. And that's the whole point of the challenge.
This is Project Feed 1010.